What up, what up? It's the math teacher Goat, and today we are doing a full lesson in AP Precalculus on polynomial functions and complex zeros. That's section 1.5, baby. These notes are a little bit longer than usual. I don't know if this is going to be under 30 minutes, but you know what? Whether it is or isn't, we're going to have fun anyway. Speaking of notes, make sure you go to the description and download those things. I'll wait. Okay, thank you. And like and subscribe and leave a comment how much you love me and blah, 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 blah. Please do subscribe, though. It goes a long way. I beg you. Now, right into the notes, we have a calculator problem. I hate using the calculator, but that's all right. Two truths and a lie. I'm going to ask you to graph that. Now I'm going to use the TI-84 Plus calculator. If you want to use Desmos, hey man, be my guest. But you're going to see me do the TI-84 Plus calculator. We're going to graph that guy, and we're going to see which two are true and which one is the lie. Okay, so let's do that. Let's run to the calculator. Do it now. All right, let's see what our lie is. First off, we are graphing f of x equals negative x times the factor x minus 3 times the factor 5x plus 4. So this is our negative button. Don't hit the minus sign. Here's our x button. Make sure you do that. Parentheses x minus 3, parentheses, open them, 5x plus 4. Now, what we're trying to find is three things. The x value for the relative minimum, which you talked about in a previous lesson, is less than the x value for the relative maximum. So we'll do that first. See if that's true or false. The zeros are 0, 3, and negative 1.25. And we'll see if the rate of change of the rate of change of the rate of change is the same. I wonder what that means. All right. Well, we have ourselves a cubic. Okay, we have ourselves a cubic, which answers the red guy, or if you or, are colorblind, it's gray. But it says here the x value for the relative minimum is less than the x value of the relative maximum. Here's the relative minimum. The relative maximum is going to live up here. So the x value for the relative minimum is indeed less than the x value for the relative maximum. That is a true statement. Okay, the other thing that we're looking at are the zeros. Are x equals 0, 3, and negative 1.25. So I see 0. It does look like 1, 2, 3. Now the other question is negative 1.25. So why don't I do this? I don't see that well. I have terrible eyes. Let's zoom in a little bit. So we're going to zoom in. We're going to hit zoom 2. I'm going to move to the left a little bit so I can focus on that number right there, which could potentially be negative 1.25. And I'm going to hit enter. Okay, so there is another 0 that lives right there. The way you find a 0 wherever it crosses the x-axis is you hit second calc 0. So you can hit 2, or you can go down to 2 and hit enter. And we're going to move our left cursor until we see it go to the left of our... I'm going too far, aren't I? Oh my gosh. Where is it? Where's my cursor? Where is it? There you are. So we have to make sure that our cursor is to the left of our 0. Then we hit enter. Then we go to the right, make sure our cursor is to the right of our 0, hit enter, and we don't get negative 1.25. We get negative 0.8. So the green is the lie. The truth here is also the red, because the rate of change of the rate of change of the rate of change is the same, which implies that it's cubic, and it is cubic. By the way, if I want to fix my zoom, hit zoom 6. There you go. That's a cubic function. And we know that because we could just do negative x times positive x times 5x and get negative 5x cubed. But yeah, that should answer that. I'll see you back in a minute. All right, so the lie here was the guy in green. You were the lie, because it actually went through negative 0.8. So that's where it went wrong, negative 0.8. Let's mess around with our calculators again, because why the heck not? All right, so what we're supposed to do is we are going to use our graphing calculator to graph both of these. So we're not going to be super specific. In fact, what I might do is I might use the calculator to graph one. And then maybe since, Desmos is now getting some traction, we'll use Desmos to do the other graph. All right, so we'll use the TI-84 Plus for this guy. We'll use Desmos for this guy, and you pick and choose whichever one you want. So let's run to our calculator again. All right, so we are graphing f of x equals x minus 3 squared times x plus 4. So here's y equals parentheses x minus 3 in parentheses, and then we're going to square that guy. The square button lives right here. Click that. And then we're going to do parentheses x plus 4. Graph. Now we have a cubic, and obviously we're sketching, so we're not looking for perfection, but what we see is we go up through what appears to be -4, goes all the way up here where we can't see it, come back down, and bounces right off of what appears to be 3. So if you're looking at what we have, it went through -4 when it was just x plus 4. But for some reason, there's something about x minus 3 that it bounces off and ricochets off. I wonder if it has anything to do with that exponent. I don't know, but let's go back and let's sketch this. All right, dudes, so we're not looking for perfection, we're just looking for accuracy. All right, what it appeared to happen is we went up through here, came back down, and bounced off of something. Now, we went through -4. And if you remember Algebra 2 well enough, that -4 is coincidentally the opposite of that +4. Now, what also happened is it ricocheted right off of here at 3. Now, 3 is the opposite of -3. Very interesting. But instead of going through, it hit the x-axis, it ricocheted off and bounced back up. So let's see if similar things are going to happen when we do this guy right here. All right, so we're using Desmos this time around, just straight up Desmos graphing calculator, nothing fancy. What are we calling it? G of x. So G of x equals negative parentheses x plus 1, close parentheses. We'll do the little thing where we can put the squared in, move to the right, x minus 4. Oh, that's a 5, x minus 4. Bang. So we see a lot of the ricochet happening again. Okay, so the ricochet is going to happen again. And this time the ricochet is happening at -1. Okay, now it starts from the top, hits -1, doesn't go through, and then comes back down and does go through 4. So let's graph this out, analyze it, and see why maybe this all happened. All right, so this time around what happened is let me get my marker. We started up here. Okay, started up here. And then we bounced off at -1. Came back up and then went down through +4. Okay, now first off, why did this start from the bottom and end up here? Oh boy, because positive x. Okay, we saw from the previous lesson, if I wanted to find out what this was, I can do x times x times x and find out that it's x cubed. Similarly, I could do -x times x times x times x, and this is -x to the third, and so it starts up here. Now, when our exponent attached to the factor was 2, it bounced off of the opposite number inside. So it bounced off at -1. When this was a regular factor, it went through 4. So we're going to talk about this phenomena just a little bit, but let's name some things before we do, stuff that you should already know. All right, if we have P of A equals 0, what this is saying right here is if we plug in some number called A for x and get 0, A is a 0 of P. If it's a 0 of P, that means it crosses through the x-axis, so it's an x-intercept. And that happens at the point A, 0. So if you plug in 3 and get 0, that means 3 is a 0. All right, and if 3 is a 0, then you have a 0 that lives at 3, 0. And that goes through an x-intercept. If A is a real number, then x minus a is a factor of p, the polynomial. All right, now what we're going to do is we're going to use this information to try to graph this guy right here. Okay, I'm not running to my calculator. I don't wanna, I don't need to, so I'm just going to do this. Now, one thing that I see right away is this is factorable. I can rip out an x. So I can rewrite this as x times the quantity, take out an x, making you x squared, take out an x, making you negative 2x, take out an x, making you negative 8. Now what I also notice is you could factor this out further, okay, to two numbers that multiply out to negative 8, so it has to be positive and negative, yet add up to negative 2 are going to be x minus 4 and x plus 2. Now using the zero product property, I know that u are a 0, so x equals 0 is a possible solution, x equals 4 is a possible solution, and x equals negative 2 is a possible solution. So I have three intercepts. Okay, I have three intercepts, and those are going to be 0, 1, 2, 3, 4, and negative 2. This is a positive cubic. So I don't know exactly what this is going to look like, but this is going to start down here, come on up, come on through, go down, and come on up. Is that absolutely a perfect picture? No, not even close. In fact, this should have dipped down a little bit lower, but I'm not really good at drawing these things. Sue me. Now here's another one. Given the polynomial h of x equals x squared minus 2x minus 3, what are all the intervals on which h of x is greater than or equal to 0? So what I do here is I do the same exact thing, all right? I'm going to factor that out. No x's are going to come out. But what I do see is two numbers that multiply out to negative 3 and add up to negative 2 are going to be x minus 3 and x plus 2. 1, just joking, x plus 1. Using the zero product property, x is going to equal 3 and negative 1. So I'll put a dot at negative 1. I'll go over here and put a dot at 3. Since u negative 3 are just kind of standing alone, okay, what that tells us is we are going to have a y-intercept at negative 3. So here. So this is a quadratic, which means it's a parabola. So something like this happens. Again, are we going to get perfection? No, I'm awful at drawing these out, but we're going to get something like that. The question being asked is, where is this function greater than or equal to 0? Well, greater than or equal to 0 means it hits the x-axis and goes above the x-axis. So that seems to happen all the way from negative infinity. Oh my gosh. Negative infinity all the way up to negative 1 and including negative 1, because you're going to include negative 1. Then we're going to say union. Then all of a sudden at 3 all the way to infinity. That is when we have ourselves positive values for h of x. Now what we didn't see is that little bumping that we saw in the previous two calculator problems. Well, that's what's going to happen here. If a linear factor x minus a is repeated n times, the corresponding 0 of that polynomial has a multiplicity of n. So you would look at this and you would say that we have three zeros. We have x equals negative 1, but then we would say the multiplicity is 2. This is going to have x equals 3, but then the multiplicity is 3. This one we have x equals negative 4. No multiplicity or multiplicity of 1, we don't even need to bother saying it. Now, one of the things that's going to happen, that bumping, you may have noticed that the bumping seemed to happen whenever you had a square exponent. Well, if you have an even exponent or an even multiplicity, that's when you're going to ricochet off. So the even multiplicity gives you that ricochet. Okay, so if I were to graph this, all right, I have negative 1, I have 3, I have negative 4. Okay, now what is this? What's the degree? Well, I have 1, 2 x's here, 1, 2, 3 x's here, and 1 x here. So this is x to the 6th. Positive x to the 6th, which means something like this is going to happen. So since my multiplicity at -1 is 2, and my multiplicity at 3 and -4 are odd, I'm going to have the bouncing off at -1. I'm going to have going right through at -4 and 3. So this is going to start up here somewhere, okay, and go through it. Now what's going to happen is we're going to bounce off, okay? We're going to bounce off, come down here, and I don't know what's going to happen. We're probably going to have a bump somewhere here, so I'm just going to put a little question mark. But what is going to happen is it's going to go up through regular 3. Why is it going through regular 3? Because the multiplicity is odd. So when the multiplicity is even, you ricochet off. When it's odd, you don't. Okay? That completes page 2. This is a big one. Okay, lots of notes for this guy. So, given the polynomial function p of x equals x minus 2, x minus 5 to the 4th, and x plus 7, what are all the intervals on which p of x is less than or equal to 0? So what I'm going to do is I'm going to draw myself a sign chart. Okay, I really don't care what the picture looks like. I just care where it's positive or negative. So I'm going to make myself a p of x sign chart. What are the numbers that seem to matter? 2, 5, and -7. More importantly, 2 has a multiplicity of 1, 5 has a multiplicity of 4, and -7 has a multiplicity of 1. Okay, so our key numbers are -7, 2, and 5. This is a 1, 2, 3, 4, 5, 6 degree thing. So once again, since everything's positive, this is going to happen. I don't care about the bumps though. What I do know is it starts up here and it's going to go and hit -7. Now when it hits -7, it goes through because the multiplicity is 1. So that happens. I don't know what happens down here, but what I do know is it's going to go through 2 because the multiplicity is 1. So that's going to happen. It's going to have to come back down, and once it hits 5, it's going to bounce off because of the even degree, the even multiplicity. So there should be bumps somewhere around here. We'll deal with that when we deal with this. But right now, this is what we know. These are the values. So I'm asking you, when is this going to be less than or equal to 0? So this is going to be a weird answer. You ready? It's going to be equal to 0 in 3 spots, u, and u. It's going to be less than 0 in 1 spot, u. So that u is going to be including -7 through 2 and including 2. But also I care about when it's less than or equal to 0. So I also have to include the fact that 5 is a possible option. So my answer isn't just an interval, it's also a point. Isn't that something? It sure is. All right, complex zeros. Let's talk about those. A polynomial of degree n has exactly n complex zeros when counting multiplicities. Okay, so let's talk about that. Complex refers to both real and non-real zeros. You might remember imaginary numbers. Okay, imaginary number is the square root of -1. Okay, so that's what we're talking here. They're in the form a plus bi. That is what a complex number looks like. Okay, we're not going to get into that too much, but what's going to happen is you may have noticed with the bouncing off of here, you know, if this is to the 6th power, we should have like 6 answers, and we don't. We don't at all. So there's confusion there. All right. If there are any non-real zeros, they always come in conjugate pairs, and we'll see the explanation below. This means there are either 2 non-real zeros or an even amount of non-real zeros. Okay, so I will say it now. If a plus bi is a 0, then a minus bi is its conjugate. So when we look at something like this, a quadratic in degree 2, it could go through the x-axis, right, twice, in which case we have 2 real zeros and no non-real zeros. It could hit once, in which case we would have 1 real zero with a multiplicity of 2 and no non-real zeros, or if it never crosses the x-axis, we'll have no real zeros but 2 non-real zeros. Now let's take a look at a cubic. It could go through it 1, 2, 3 times, which means no non-reals. It could go through it once and have 2 non-reals, or it could go through it twice and have no non-reals, but this twice is going to have a multiplicity of 2. So you're going to have one that has a multiplicity of 1 and one that has a multiplicity of 2. But again, what we're noticing is in nowhere did we have an odd number of non-real zeros. So let's try to understand that. The degree of a polynomial is 8, with zeros at x equals -10. That's 1, 5, 16, and is that it? Oh, and 5 has a multiplicity of 2. Okay, so bang, bang. So real zeros at -10, 5, and 16, and then a multiplicity of 2. So hold on, dumb me. I kind of accidentally counted this guy twice, so I made it super confusing. What we have is we have 3 real zeros, but it counts as 4 because of the multiplicity, which means we're going to have a leftover of 4 non-reals. Now again, what you do is you take the polynomial, and the polynomial tells you that's how many complex zeros you're going to have. You take away the number of real zeros, and that's what you're left with for non-reals. Okay, now I brought this up, we're bringing it up again. If a plus bi is a non-real zero of the polynomial p, then its conjugate a minus bi is also a zero of p. Okay? All right. Moving along. So easy questions. Given the non-real zero of a polynomial, find another zero. Well, if one of them is -3 plus 6i, then the other one is -3 minus 6i. And if one of them is 4 plus 2i, then the other one is 4. Did I say 4? 4 minus 2i, the other one is 4 plus 2i. All right, let's bring back an old friend, shall we? Find the degree of the polynomial from the given input and output values. So what we're going to do is we're going to do the whole linear thing, see if it adds up to the same number. If no, then try quadratic and go from there. So what do? We add 1, we add 3, so it's not linear. We add 5, we add 7, we add 9, we add 11, we add 13, like so. So it's not linear, it's a quadratic. What do? You add 2, you add 2, you add 2, you add 2 again, you add 2 again. And the question is find the degree. The degree is 2, because it's quadratic. Oh, good to see you, old bouncing equal length input value interval problems. Oh, we're doing it again. Find the degree of the polynomial from the given input and output values. All right, so let's do it again. We have ourselves another table, and we're going to do the same thing. Find the degree of the polynomial. All right, so let's do it. Let's subtract 1. Let's subtract 11. Let's subtract 33. Let's subtract, 67. Let's subtract 113, I think. Yep, let's subtract 171. Let's subtract let's subtract 241. So is it linear? No. Is it degree 1? No. Quadratic. Let's subtract 10. Let's subtract 22. So it ain't quadratic either. Let's subtract, 34. Let's subtract 46. Let's subtract 58. Let's subtract 70. Non-quadratic, not linear. Is it cubic? Let me see. To get from -10 to -22, subtract 12. To get from -22 to -34, subtract just to make sure we don't screw up. Hooray! So over equal length input value intervals, we have not linear, not quadratic, but cubic. This is a degree 3. Boys and girls, degree 3. I made a rhyme. All right. Lots of the same stuff, but we're just, doing a little bit more. We're going to make ourselves sign graphs out of this based off of what we have. So I need to find out when p of x is less than or equal to 0. So I have an x here. I have 2 x's here because it's squared. This is a positive cubic, so it's going to look like this. Okay? Here I have zeros existing at regular 7 and regular 1, but at 1 there's a multiplicity of 2. So making a sign graph of p of x, okay, we could put numbers at 1 and 7. And I know it's going to ricochet. It's going to start down here, bounce off the 1 because the multiplicity is 2, bounce off the 1, come back down, and head back up and hit the 7. So it's going to look a little something like this. Bounce up. So I care about when it's less than or equal to 0. Well, it is 0 here at 1. It is 0 here at 7. And it's less than between 1 and 7. Oh, but you know what else? It's also less than from regular 1 to the left. So all the way from negative infinity through 1 and all the way up to 7, and including 7, are we less than or equal to 0? So that's how you do that. Let's do it again. This one's already given to us as a positive cubic, so again, I'm going to look something like that. But I need to factor things out, so let's rip out an x. That leaves us with x squared plus 9x plus 18. That looks like a perfect square trinomial because oh, is it? No, it's not. I was wrong. I was wrong. If you add 6 and 3, you get 9. If you multiply 6 and 3, you get 18. So this is plus 6. And this is plus 3. So my zeros are going to be 0, negative 6, and negative 3. Okay, no double multiplicities anywhere. So we care about magic happening at negative 6, magic happening at negative 3, and magic happening at 0. Okay, this is a cubic, again, so it looks like that. So it's going to start from the bottom. Okay, go through negative 6, come back down, go through negative 3, go through 0, and nothing fancy at all happens. We care about when it's positive and also 0. So it's 0 here, here, and here. It's positive between negative 6 and negative 3, but also positive from 0 on. So we are going to say that including negative 6 and going through negative 3, it's positive, union. And from 0 to infinity, it's also positive. Yeah. All right. Now what? Let's blow it up. Okay, blank functions are symmetrical over the blank. If you can see, we have things that seem to reflect left to right. Like if you were to take this and fold it over left to right, you would have the same exact image. Well, what are these called? These are called even functions. Even functions are symmetrical over the y-axis, which means the y-axis acts as a mirror. So these are graphs of even functions. Now, if you're thinking, I know what's going to happen next, odd functions. That's right. They are symmetrical over the origin. Now, that's kind of hard to view. You're like, well, what does that even mean? Basically, the origin is right in the middle, so everything kind of spins around each other. To me, the best way to visualize an odd function, right, is if you were to take this guy and spin it upside down, do you get the same image, right? You do. If you were to take this guy and spin it upside down, would you get the same image? Yes. If you take this guy and spin it upside down, would you get the same image? Yes, you would. So that's how I view an odd function. I don't like saying it's symmetrical over the origin, but technically, you're right. So an even function is graphically symmetric over the line x equals 0. Again, that means the y-axis. Analytically, it has this property right here, that if you were to do f of negative x, you will also get f of x. Now that looks strange. What does that mean? That means if I give you a function, as you're about to see here, and I plug in negative x for every x, I get the same exact function that I started out with. You can prove that a function is even by substituting negative x and see if you get the same original function. All right, so we are going to show that this guy right here, let me blow it up just a teensy bit. We're going to show that that guy right there is an even function by doing just that. So f of x is x to the 6th minus 4x squared. What happens if I replace every x with negative x? Well, that'll look like negative x to the 6th minus 4 parentheses negative x squared. Simplifying, negative x times itself 6 times is back to x to the 6th power. Minus 4 doesn't change. Negative x times itself is still x squared. X to the 6th minus 4x squared is x to the 6th minus 4x squared. This, ladies and gentlemen, is indeed an even function. Okay? Now there's a shortcut down here that we're going to use, but we're not going to go there quite yet. We're just going to do the analytical version, and then we'll do the cheat version. Okay? An odd function, as we mentioned before, is symmetric over the origin, which is the point 0, 0. Okay, now listen, if I wanted to go back here, I will attempt, I could draw this out, right? And that's probably what I should have done here. Okay, that's probably what I should have done here, where I had this guy, and I need to show that, all right, if this is an even function, basically this is going to come back up here, come back down here, and make its way that away. So it's going to look like you. Oh my God, I'm so bad at doing these. But I tried. Okay, now odd. This is going to be awful for me to draw, but I'm going to try my best. Okay, it's symmetrical over the point 0, 0, which means if I were to spin this upside down, I'm going to get the same image. So I'm going to take this point right here, which appears to be 1, negative 2, and I'm going to make it negative 1, positive 2. I'm going to take this point here, which appears to be 2 down 1, 2, 3, 4, 5, 6, 7, 8.5. So right 2 down 8.5. I'm going to go left 2 up 1, 2, 3, 4, 5, 6, 7, 8.5, and go right there. And then it's just going to come back down. So this is going to look like this, come up here, and then come back down. Poorly, but you get the idea. Now, analytically, what this looks like is if I were to substitute every x with negative x, if I were to plug in negative x for every x, what I'm going to get in return is the exact opposite of what I started out with. So if I start out with something like 3 plus 18, it's going to be negative 3 minus 18. That's the exact opposite. So I'm going to show, and by the way, the exact opposite of this would be positive 2x cubed minus 5x. So you could prove that a function is odd by substituting negative x and seeing if you get the opposite. So let's see if I plug in negative x to every x here, if I get positive 2x cubed and negative 5x. So f of negative x is going to be negative 2 times negative x to the 3rd plus 5 times negative x. Negative 2 is negative 2. Negative x to the 3rd is going to be negative. So you're going to bring out a negative there, right? Negative x to the 3rd. All right, so you might be thinking, what did you do here? Nothing really. But this becomes negative 5x. So a negative times a negative here is a positive, so we get positive 2x to the third minus 5x. Is positive 2x to the third the opposite of negative 2x to the third? Yup. And is negative 5x the opposite of positive 5x? Yup. And so this is odd, or yup. Now, what happens if you plug stuff in, if you plug in negative x and you neither get the same nor the opposite? Well, that's when it's a neither. So I'm going to show you that this is a neither. So f of negative x is going to be 6 times negative x to the fourth minus 2 times negative x. Okay, negative x to the fourth is positive x to the fourth, so you become positive x to the fourth. Negative 2 times negative x is positive 2x, and at the end of the day, we get 6x to the fourth plus 2x. 6x to the fourth is the same as 6x to the fourth. Negative 2x is opposite of positive 2x. That's where we get the neither. Now that was so much work, and I hated every second of it. Boy, oh boy. Is there a faster way that you can do this? Yup. First off, if every exponent of a variable is even, then the function is going to be even. Okay, so for example, if I give you something like f of x equals x to the fourth minus 2x squared plus 7, okay, the variable has an even degree. The variable here has an even degree. And if you're like, whoa, 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 there is no variable. Okay, it is a variable. X to the 0th is an even degree. So all of these have an even degree. So if it only has even powers of x, it is even. If every exponent of a variable, let me scroll down a bit. If every exponent of a variable is odd, then the function is odd. And that could look like g of x equals, I don't know, 3x to the fifth minus x to the 17th plus 2x. If you have a mix of odd and even exponents attached to x, well, then you have neither. Okay, so that's a little shortcut. So let's do some practice problems. Okay, I believe we're going to do 2 pages of practice problems. Let's get into it. Let's get into it. In the xy plane, the graph f of x equals x times the quantity x plus 3 cubed times the quantity x minus 2 squared, and it intersects the x-axis at how many different points? Okay, so it's going to intersect at 0, it's going to intersect at -3, and it's going to intersect at 2. Now, I don't care about bouncing off. I don't care about any of that. All I know is I have 3 zeros with multiplicities differentiating everywhere, so it's only going to intersect at 3 spots, so the answer is 3. So we're going to have some complex areas, right? We're going to have some, or maybe we won't have complex areas. In fact, we won't have complex areas. But what's going to happen is we're going to have 3 spots where it crosses the x-axis. Given the table of values, determine the degree of the function. All right, so we've done this before. Let's do it again. I have a feeling this one's not going to be as lovely as we want it to be. Look at those numbers. They're definitely not going to be as lovely as we want them to be. Let me super zoom in. I have a feeling we're going to need the space. All right, is it linear? Let me see. What do? You subtract 13. Subtract 81, I can handle that. Subtract -221. Subtract -457. I think, yep, subtract 813. So yeah, not linear. Is it quadratic? Subtract 68. -140. -236, -356, so not quadratic, not quadratic at all. Is it cubic? Please. -72, subtract 96, subtract 120. So it's not cubic either. Is it quartic? Oh, look at that, subtract 24. And subtract 24. So after all of that, we got ourselves a degree of 4. Looks pretty, though. Wasn't fun at all. The function of f is even. Which of the following equations should define or could define f? I'm not going to do the whole let's plug stuff in and get the same thing. Basically, it's got to be a... oh, I do have to. Oh, because of that. Oh, that's so annoying. Well, all right. I mean, basically the rules still should apply. I mean, you have an even variable exponent. You don't, so it can't be A. You do, so you have promise. You don't, and you don't, so it can't be C. You do, I'm sorry, you don't. You do, so it's got to be this. So basically, if I were to take B and plug in negative x, I would get 3 over 1 minus negative x squared, which just becomes 3 over 1 minus x squared. So you are even. It's B. Yeah, I was hoping to do the shortcut. I guess you could still do the shortcut, but I don't know. The shortcut, I usually think of polynomials, not rational stuff. All right, let's do this again. We've done this before. Which of the values are less than 0? So in many of the previous problems, we've done less than or equal to or greater than or equal to. Now this is just less than, so let's see if that changes the game a little bit. First things first, we know we have zeros at -2 here. That's obvious, and at 4 here, that's obvious, but not so much this guy. So if you have to, you go off to the side and do 3 minus 2x, set it equal to 0. Subtract 3 from both sides, right? And then divide both sides by -2, and that gives you positive 3 over 2. So I have zeros at 3 halves, -2, and 4. But -2 has a multiplicity of 2. So I'm going to draw myself a little sign graph for p of x. My magic number is -2, and then I have 3 over 2, and then I have 4. This is a -2x times x times x times x. -2x times x times x times x gives me a leading term of -2x to the 4th, which looks like an upside-down W type thing. So not only do I have an upside-down W type thing, it's going to ricochet off of -2 because of that multiplicity of 2. So you start from down here, start from the bottom, ricochet off, come back up, go through 3 over 2, go through 4, and go like that. I only care about where this is negative. I don't care about where it hits 0. So ignore the fact that I have that big bold red dot there. I'm going to highlight the negative parts in blue, which is here, and also here, not including -2 and not including 3 over 2. So all the way from -infinity all the way up to -2, but not including it, it's negative, union. And then starting from -2 again to 3 halves, it's also negative. And that appears to be... Oh, you know what I missed? Stupid. I missed the fact that 4 on it's also negative. Sheesh. So let's union that again and go from 4 to infinity. So that leaves us with -infinity to 2, -2 to 3 halves, and 4 to infinity. I can't believe I missed that. Because I was looking at this and I was like, what did I do? Well, I'm blind is what I did. All right. A couple more and then we can call it a day. The function q of x is a polynomial of degree 3. If q of 3 is 0, which means 3 is a 0, right? Which of the following must be true? All right, so they're saying if I plug in 3 and get a 0, which of these must be true? That if I plug in -3, I get a 0? No, that doesn't have to be true. Q of x has 1 real 0 and 2 complex zeros. That's possible, but it doesn't have to be true. Q of x can be expressed as x minus 3 times p of x, where p of x is a polynomial of degree 2. So that's true. So what they're saying is Q of x, okay, is going to look like something like this, right? Blah, 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 blah. I know that if I plug in 3, I get 0, which means I'm going to get x minus 3, which means the rest is going to be something like that, blah, 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 blah. Now, of course, there could be something in front of that. There could be something in front of that, and it doesn't really matter, though. Because what this is saying is if I plug in 3, x minus 3 is going to be a factor. Okay? Degree 5, I don't know what I'm even talking about. All right, let's finish this puppy up. The picture is a graph of g of x. True or false? Dividing g of x by 15 will change the placement of the zeros. False. Now, listen, what that means is let's say I give you something like this. 5x squared minus 15. Okay? If I were to try to find the zeros, one way that I could try to find the zeros is I can say, all right, set it equal to 0. Okay? Add 15 to both sides. Okay? It's going to look like that. Divide both sides by 15, divide both sides by 15, x squared equals 1. If I were to solve that, I'm going to get positive or negative square root of 1, so x equals the positive or negative square root of 1. Great. If I were just to pretend all of a sudden that 15 wasn't there, okay, and get x squared minus 1, okay, equal to 0, add 1 to both sides, and you're still going to get the same exact result. Same exact result, nothing changes. So if you have zeros, dividing a regular number by anything won't change what your zeros are. So it's a very bizarre problem, but the reason why I gave you this very bizarre problem is because you're going to have a very bizarre homework or AP classroom problem similar to it. And on that note, we are done. So that was a long lesson. Lots to do there, lots to do. What you really need to do is go to my YouTube. Okay, first off, like and subscribe. Please do subscribe. It goes a long way for me. But go to my YouTube and type out AP Precalculus 1.5. And then watch the problems that look like this, okay? And it'll just give you some extra stuff, extra ammo in your weapon of learning. Oh, that was cheesy as anything, but you know what? I like it. On that note, have a wonderful day. I love you. Thanks for watching. Like and subscribe. Bye.